So this is number theory, Math 316, and it will be lecture 1 in a moment. Again, all of the lectures are live on Zoom, but I record them and upload it to the YouTube channel for number theory that you'll find on the course information sheet. Sometimes I forget to press record. If you notice it's not recording, please tell me and I'll press record. Because I'd rather not miss even the first couple of minutes of each talk. So this is a real mathematics course. It's not like calculus, which is certainly real mathematics, but in calculus, you're learning techniques and you have to solve problems. You have to differentiate a function or integrate a function and just get the right answer. But in number theory, you have to prove theorems. So this is a proof-based course. There are calculations. And in fact, I am going to encourage you to learn Maple. I'll give a little talk on how to get Maple from the Maple's a computer software program, mathematics program. Some people, if you've taken Math 155 or 156, different instructors use different programs. Some instructors use Maple, which is the best of all the programs that seem to be available. It's completely free if you're a CUNY student. You don't have to buy it. You download it free from the CUNY email. And there are a lot of number theory commands in Maple that are very useful. So we'll get to that, but not for a few weeks. So let me go to my document camera so I can start to do some mathematics. So what you should see is a page and the moving pencil, Math 316, number theory, and this is lecture 1. And the textbook is a book that I wrote a long time ago called Elementary Methods in Number Theory. And the syllabus is basically chapters 1, 2, and 3. And I will, you don't have to buy the book. I am uploading these 3 chapters to Blackboard. Chapters 1 and 2 are already posted. And that is the text. And the homework are problems in the book. So homework 1 will be some problems in chapter 1, section 1 that I'll put up on Blackboard later today. But it's everything that we do is in this text. It is the classical standard beginning course in number theory. And we start with a certain, so what is number theory? We study numbers, and not just, not complicated numbers, integers. So we have the positive integers, also called the natural numbers. It's a set denoted by a capital, kind of a capital N, 1, 2, 3, 4, 5, 6, and so on. Those are the positive integers. 0 is not positive. Then we have the non-negative integers. So this is, it's denoted N0, which is the integers, positive integers N, union 0. So you have to know set theoretic notation. This is the union of 2 sets. So this is all the positive integers together with 0. And then we have the set of all integers, which is always denoted by Z. So this is the positive integers, and 0, and the negative integers. Right? So this is the substance. This is what we study in number theory, the integers. Positive integers, non-negative integers, all the integers. We can add them, we can subtract them, we can multiply them. You can't always divide them. 6 divided by 3 is 2, an integer, but 6 divided by 5 is not an integer. It's a fraction or a rational number. And we also consider sometimes the rational numbers, denoted by Q, which is just everything of the form A over B, where A and B are integers and B is not 0, right? You can't divide by 0, but so all fractions A over B, where B is a non-zero integer and A is any integer. So this is the basic material for our course. And a lot of the times we consider theorems about not all the integers, but maybe just the non-negative integers or just the positive integers. And we're going to prove things. And when you prove something, you need to start with some axiom or some assumption, some hypothesis, some principle that you can use to prove a theorem. And the fundamental...
So, Professor.
Yes, sir.
Oh, sorry. So is the n the natural numbers?
N, natural
Okay.
numbers, or
Okay,
positive integers.
Okay.
And not the positive integers and 0, so the non-negative integers.
Okay, thank you.
Yep. So there is something called the minimum principle. And the minimum principle says the following: every non-empty set of non-negative integers contains a smallest or a minimal, means the same thing, element. So if you have a set of non-negative integers, it always contains, and there's something in the set, it's a non-empty set, it always contains a smallest one. This is not true if you take the integers positive and negative, because if you take all the integers, that's a non-empty set, but there's no smallest integer. They go to minus infinity. There's no smallest integer. But if you take a set of non-negative integers, so this non-negative is crucial, it always contains the smallest element. Or you can generalize this a little bit and put it in the following form. Every non-empty set of integers, which is bounded below, contains a smallest element. And what does bounded below mean? A set S is bounded below if there exists a number, an integer, m, such that S is greater than or equal to m for every number S in the set S. So your set is bounded below if the elements in the set are never smaller than something. So if you can look at, for example, the set S equal to 3, 32, 51, minus 9, 7, minus 18. So this is a set of integers. This is contained in Z. is bounded below, for example, by minus 100. Because every number in this set is greater than or equal to minus 100. It's also bounded below by minus 50. It's also bounded below by minus 18. But this is a non-empty set of integers bounded below, and the smallest element in S is this guy, minus 18. So that's what it means for a set to be bounded below. And this seems like a very simple, very elementary, very obvious proposition or statement. But this is really the starting axiom for a lot of mathematics and really for all of number theory. And let me use this right away to prove a fundamental result in number theory. It's really a proof of what they teach you in elementary school when you learn long division. So let's see what this says. This is called the division algorithm. That A and B be integers, and B is positive. So I want to explain how you can divide A by B. So this division algorithm says there exist, so that's an important word, something exists. Unique, that's another important word. There exist unique integers, Q and R, such that A is BQ plus R, and R is an integer between 0 and B minus 1. So this says if you divide A by B, Q is called the quotient, and R is called the remainder. So if you divide A by B, you get a quotient Q and a remainder R. And remember, the only thing that has to be positive is what you're dividing by, this number B. And your remainder is between 0 and P minus 1, B minus 1. So for example, I don't know, suppose I take A equal to 35 and B equal to 11. Then if you divide 35 by 11, 35 is 11 times 3 plus 2. So my quotient is 3, and my remainder is 2, right? So again, this is just what they taught you in elementary school, long division. Divide a number A by B, you get a quotient and a remainder. And you just sort of learned an algorithm to do it. You learned how to do long division. Of course, then they invented calculators, and most people forgot how to do long division, but it's a useful technique. And here's actually a proof. I mean, I'll prove this in a moment. This is a proof that it can always be done. So I need to prove this. I need to prove Q and R exist, and then I need to prove that Q and R are unique. There's only one. So proof. So my proof will go as follows. Now, the only tool that I have to prove something is the minimum principle. That's what I started with. That's all I have. The minimum principle says a non-empty set of non-negative integers contains the smallest element. So I need to look for a non-empty set of non-negative integers. So I'm going to define a set S be the set of all numbers of the form A minus BQ. So A and B are fixed. We have no choice about that. A and B are given, where Q is an integer. This means Q is in the set of integers. And A minus BQ is greater than or equal to 0. So I'm going to look at all numbers of the form A minus BQ as Q runs through all the integers, but I only take the numbers A minus BQ, which are non-negative. So first of all, I have to show that S is not the empty set. So this symbol is the empty set, the set that has nothing in it. All right. I have to show there's always some number of this form. So let's divide this into two cases. So in case 1, the number A could be negative, but suppose A is greater than or equal to 0. So in that case, choose Q can be any integer, choose Q equals 0. So then A minus BQ, if Q is 0, A minus BQ is just A, which is greater than or equal to 0. So A is in S. So if A is non-negative, this set certainly contains something, some integer. The little trickier case is the case when A is negative. Right? So if A is negative, in this case, choose Q to be a negative number. Let's say we choose Q to be equal to minus capital Q, for Q greater than or equal to 1. So if A is negative, I choose Q to be a negative number. And then what is A minus BQ? A minus BQ is A minus B, and little q is minus capital Q. And minus times minus is plus. This is A plus BQ. And what is this? So B we know is positive. Q is positive, but A is negative. But A is fixed. And as Q gets bigger and bigger and bigger, this positive number, sooner or later, is bigger than the absolute value of A. Like if A is minus 100, even if B is 2, at some point 2Q is bigger than minus 100 for some Q. So this is going to be greater than or equal to 0 for some Q. And in that case, A plus BQ will be in S. So whether A is positive or negative, this set S does contain some non-negative integer. So S write down this from the beginning. So S, which is everything of the form A minus BQ, Q an integer, A minus BQ greater than or equal to 0, is not the empty set. This is just a mathematical way of saying that S is non-empty. By the minimum principle, S contains the smallest element. I'll call it R. So R is the smallest element in S. So R is in S, which implies, that symbol means implies, A minus BQ equals R for some integer Q. Because everything in S is of the form A minus BQ, we call the smallest number in this set R. So R is A minus BQ for some Q. So if I just take the BQ from the left to the right-hand side of this equation, A is BQ plus R. So I have a representation of A in the form BQ plus R of the kind that I was looking for. But I have to show the second part of the division algorithm is hold. I must prove that R is less than B. R is an integer between 0 and B minus 1. I still need to prove this. Let's do, so we know R is non-negative. We just have to show that R is less than or equal to B minus 1. So let's do what is called a proof by contradiction. Suppose this is false. If this is false, R is greater than or equal to B, right? R is an integer. If it's not, and it's non-negative. If it's not less than or equal to B minus 1, it's greater than or equal to B. But then, what can we say? So then, A minus A is BQ plus R. Then we write this as BQ plus B plus R minus B. I just added and subtracted B. This is B times Q plus 1 plus R minus B. So if I subtract this from both sides, A minus B times Q plus 1 is R minus B. Now, R is greater than or equal to B. So R minus B is greater than or equal to 0. But R minus B is a number of the form A minus B times some integer Q minus 1. So this means that R minus B is in S. Of course, the set S is all non-negative integers that you can write as A minus B times something. But B is positive. So R minus B is strictly less than R. Because I'm taking R and I subtract something positive, I get something smaller. R minus B is strictly less than R and greater than or equal to 0. And that is a contradiction. Because R is the smallest element of S. And I just picked something, found something smaller than R, namely R minus B in the set S. That's a contradiction. So you can't have a contradiction in mathematics. And we got a contradiction by supposing that R is greater than or equal to B. So it's not. R is less than or equal to B minus 1. Okay. So this is a very important method of reasoning in mathematics, and in particular in number theory. And when you see a proof, often it's a little bit mysterious at the first time you see it. So you need to study it, and maybe it still is mysterious, and that just means you need to study it some more until it becomes a little bit clearer, and you can watch this proof on the video as often as you want, and also ask questions. So what we just proved is that this remainder R is in the right range between 0 and b minus 1. So I haven't finished proving the division algorithm, but I did prove the first half. So what I just proved is that given integers a and b, with b positive, again, positive always means greater than 0. 0 is not positive. 0 is not negative. 0 is special. 0 is 0. But given integers a and b with b at least 1, there exist integers q and r such that a is bq plus r and r is greater than or equal to 0 and less than or equal to b minus 1. So this is the proof of the existence. But I also claim that the quotient q and the remainder r are unique. Why is that? So uniqueness, this is what I have to prove. Suppose we also have, suppose q and r are two numbers that satisfy this. And suppose we also have q1 and r1 such that a is equal to b q1 plus r1. And r1 is also between 0 and b minus 1. So we have this representation of a and this representation of a, and they're equal. So we have that bq1 plus r1 equals a, which is equal to bq plus r, right? Because they're all equal to a. So let me rearrange this. bq1 minus bq is r minus r1. Just brought this over to this side and this over to this side. And if I factor a b out of this, b times q1 minus q is r minus r1. What do I have to prove? I have to prove that q1 equals q and r1 equals r. I have to prove that the quotient and the remainder are unique. So I have this equation. If q1 is different from q, then q1 minus q is a non-zero integer. So at least in absolute value, this is at least 1. Right? So if I look at the absolute value of the left-hand side of this equation, b is positive. b times q1 minus q is at least b. This is b times some positive integer. So this left-hand side is at least b. But what about r minus r1? Here I have 0 and b minus 1. And r and r1 are two numbers in this interval. What's the biggest distance apart they can be? You could have r bigger than r1 or r1 bigger than r, but the absolute value of r minus r1, the distance between these two, is at most the distance from this left hand to this right hand side of the interval, is at most b minus 1. But now we have a contradiction because we have, on the one hand, b times q minus 1 minus q is r minus r1. So if two numbers are equal, their absolute values are equal. The absolute value of R minus R1 is at most B minus 1. But if Q1 is different from Q, this is a comma, not a 1. If Q1 is different from Q, then we saw that B times Q1 minus Q is greater than or equal to B. So I have an inequality that says B is less than or equal to B minus 1. And this is absurd. A contradiction. Well, the number B can't be less than or equal to B minus 1. And what gave rise to this contradiction? The assumption that Q1 was different from Q. So therefore, Q1 equals Q. And if Q1 equals Q, this is 0. So Q1 minus Q is 0. So B times Q minus 1, Q1 minus Q is 0, but B times Q1 minus Q is R minus R1. So this means that R equals R1. And we're done. We prove if you have two representations of A as BQ plus R, where the remainder is between 0 and B minus 1, then the quotient Q and the remainder R are unique. So we just prove uniqueness. Okay. So this is the division algorithm. It's something which is completely basic. And again, you know this because you've been doing long division for years and years and years. You take a number, you divide it, and you get the quotient and the remainder. And there'll be a couple of homework problems where you actually have to do the calculation, preferably by hand, but use a computer or calculator, it's okay. On exams, though, you can't use calculators or computers. You have to do things by hand because it's important to know how to do these kinds of calculations by hand. But this is the division algorithm. Any questions about this? Someone had asked if you can prove the minimum principle. No, it is an axiom. It's an axiom. You have to start with something, and in number theory, this is really what we start with. Now, so the only mathematical principle of reasoning we used to prove the division algorithm was the minimum principle. There is a second method of reasoning in number theory that we use.
Professor,
Yes, sir. Yes.
is that a 1R equals R1?
R equals R1.
Oh, no, is that a 1 next to the R, from your left?
Where my pen is?
No, next to it. Here. Is this a 1 right here?
This is R. This is R sub 1.
Okay. Oh, okay, I see. Thank you.
So there's another consequence of the minimum principle, which is called the principle of mathematical induction. And this is a method of proving statements, proving theorems, not just in number theory, but everywhere in mathematics. And it says the following thing. So the statement is a little bit abstract in the beginning, but then I will give some examples to make it a little bit more concrete. So suppose we have S of n is some statement or proposition, some assertion about the integer n. So if the following two situations hold, if S of 1 is true, that is, if you let n equal 1, the statement is true for n equal 1. And if the truth of S of n implies the truth of S of n plus 1 for all n, then the statement S of n is true for all n. So let's see, what does this mean? So first of all, S of 1 is true. That's given, right? S of 1 is true. Therefore, if S of 1 is true, then S of 2 is true. So S of 1 implies S of 2 is true. Because if something is true for n, it's true for n plus 1. But if it's true for S of 2, it's true for S of 3. But if it's true for S of 3, it's true for S of 4. And if it's true for S of 4, it's true for S of 5. And you can imagine if you continue this forever, you see that S of n is true for all n. And that's exactly what the principle of mathematical induction says. If your statement is true for 1, n equal 1, and if whenever it's true for a number n is true for the next integer n plus 1, then it's true for all n greater than or equal to 1. And in this, you didn't have to start with 1. You could have started with 0. If you knew that the statement S of 0 was true, and then whenever it's true for n is true for n plus 1, then it would still be true for all n greater than or equal to 0. Because we would say S of 0 is true. And because S of 0 is true, S of 1 is true, and then you just continue along this way. So your starting point might be the statement about 0, or it might be the statement about 1. In fact, you could have any starting point, and then your statement is true for all subsequent integers. So this is the principle of mathematical induction. And let's look at an example. So let S of n be the following statement. It is S of n is the assertion that the sum of the first n integers, sorry, that's not what I want to say. Actually, why not? The sum of the first n integers is n times n plus 1 over 2. Why not? Let's just check. What is the case n equal 1? So what is the sum of the first one integer? 1. And if you let n equal 1 in this equation, you get 1 times 1 plus 1 over 2 is equal to 1. So S of 1 is true. The sum of the first integer, first n positive integers, is this. What about n equal 2? So the sum of the first two integers is 1 plus 2, which is 3. When n is equal to 2, what is this? 2 times 2 plus 1 over 2 is 2 times 3 over 2 is 6 over 2 is 3. So this statement is correct for n equal 2. What about n equal 3? This is just to give you a feeling that the statement really is correct. What does S of 3 say? Take the sum of the first 3 integers. That's 6. What is this formula when n is 3? This is 3 times 3 plus 1 over 2 is 3 times 4 over 2 is 12 over 2 is 6. So this equals this. Still is true. What about n equal 4? So S of 4 says add the first 4 integers, you get 10. What is this when n equals 4? 4 times 4 plus 1 over 2 is 4 times 5 over 2 is 20 over 2 is 10. So it checks. So we can see this statement is true by explicit calculation for n equal 1, 2, 3, and 4. But now let's try and prove it for all integers in one fell swoop using the principle of mathematical induction. So assume true for n. That is, assume that S of n, which is 1 plus 2, this is the sum of the first n integers, is n times n plus 1 over 2. We must prove the statement, or we must prove the statement is true. We must prove S of n plus 1. Let's try and prove it. What is S of n plus 1? This is the sum of the first n plus 1 integers. The sum of the first n plus 1 integers is the sum of the first n integers plus n plus 1. But the sum of the first n integers by the induction hypothesis is this. It was this plus n plus 1. I can factor n plus 1 out of this. I get n over 2 plus 1. Then we do some elementary algebra. This is n plus 1. N plus 2 over n plus 1 is n plus 2 over 2. And what is this expression? This is n plus 1. N plus 2 is the same as n plus 1 over n. That's exactly this formula with n replaced by n plus 1. That's what we had to prove. So we're done. This square box means end of the proof. We're done. Okay.
Professor, you can push the paper down a couple of seconds.
Yeah, that's it. That's the end of the proof. So that's our first example of proving something by mathematical induction. We proved the sum of the first n positive integers is n times n plus 1 over 2. Any questions about that?
Can you give us a second? I'm gonna finish writing the bottom part.
Mm-hmm. Okay, let me continue. Let's look at another example. So suppose S of n is the statement the sum of the first n odd positive integers is miraculously n squared. Let's see, let's check the first few cases. What does S of 1 say? Well, the first odd positive integers is 1, and 1 is equal to 1 squared. So it's true. What does S of 2 say? Take the sum of the first two odd positive integers. 1 plus 3. 1 plus 3 is 4. That's 2 squared. What is S of 3? The sum of the first three odd positive integers. 1 plus 3 plus 5. That's 9. That's 3 squared. What's the sum of the first four odd positive integers? Add it up. You get 16. That's 4 squared. That's a miracle. What about S of 5? If you take the sum of the first 5 positive integers and you add it up, you get 25, which is 5 squared. So this statement is certainly true for n equal 1, 2, 3, 4, and 5. So we know that it's true for 1. We must show that if it's true for n, that S of n implies S of n plus 1. So suppose S of n is true, we must show S of n plus 1 is true. What does S of n say? S of n says the sum of the first n odd positive integers. What are they? 1 plus 3 plus 5 plus 7. What is the nth positive integer? 2n minus 1. When n is 1, this is 1. When n is 2, is 3. This is the sum of the first n positive integers. And the induction hypothesis says that this is equal to n squared. So now let's consider S of n plus 1. For S of n plus 1, this is the sum of the first n odd positive numbers. And if you add 2 to this, you get the next positive number that's odd, which is 2n plus 1. So this is the sum of the first n plus 1 odd positive integers. This part is equal to n squared. So we have n squared plus 2n plus 1. And this you should recognize. N squared plus 2n plus 1 is n plus 1 squared. So that's the whole proof. We're done. If the sum of the first n odd positive integers is n squared, then the sum of the first n plus 1 odd positive integers is n plus 1 squared. So this is true for all n.
Professor?
Yes.
Hello. How did you get in the second step? How did you get 2n plus 1?
Here?
No, no, like second step. How did you get
Here?
here?
I don't know. What's the first step and what's the second step?
No,
So
no,
which
it
line are you looking at?
says 2n plus 1. It says 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1.
Here.
Yeah. How'd you
Okay.
with that?
So this is the sum of the first n odd positive integers.
Yeah.
Right. So this say in general, the nth odd positive integer,
I can't see the. Yeah, sorry.
the nth odd positive integer is 2n minus 1.
Okay.
Like what's the fourth odd positive integer? 7. Plug in n equal 4 here, you get 8 minus 1, you get 7. This is the nth odd positive integer. So here I'm looking at,
Professor, we can't see the line.
sorry?
We can't see the line. It's not showing. It's like it's covered off.
I'm sorry, what line is cut off? It's all here.
At the bottom. Can I see the bottom while you are talking
This
about
is the bottom.
that top?
That's the
No, I'm
top.
saying we can't see it. Yeah, the bottom. Yeah, right there. Thank you.
This is the bottom. So the nth, for any n, the nth positive integer is the number 2n minus 1. So if I'm looking at the first n plus 1 positive integers, so if this is the nth positive integer, the n plus first odd positive integer is 2 times n plus 1 minus 1, which is 2n plus 2 minus 1, which is 2n plus 1. This is the nth positive integer. This is the n plus first positive integer. Okay. That's the proof. Let's look at a couple more examples of using mathematical induction. So in many parts of mathematics, and especially in computer science, you write integers to base 2. So what this means is that every positive integer is uniquely the sum of distinct powers of 2. So what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, and so forth. 128. So let's take a number, a random number, 291. Let's see, that's an integer. I want to write it as a sum of powers of 2. The largest power of 2, let's see, after 128 comes 256, 512. I can write this as 256 plus 35, I think. 256 is a power of 2. 35 is not. But 35 is 32 plus 3. And 3 is 2 plus 1. So 295, let me write it in the opposite order, is 1 plus 2 plus 32 plus 256. That's 1, which is 2 to the 0th power, plus 2, which is 2 to the 1st power, plus 32, which is 2 to the 5th power, plus 256, which is, I think, 2 to the 8th power. So here I've written 291 as a sum of distinct powers of 2. Here, everyone should have paper and pencil. Here's a number. Right, 584 as a sum of distinct powers of 2. So I'll give you a second and you do that. Oh. So what's the largest power of 2 I could pick in this representation?
2 to the 9th.
Sorry?
2 to the 9th.
Which is what? What is 2 to the 9th?
512.
Okay, 512. This is 512 plus what, 72. So what's the next power of 2 I would pick from? Simplest thing is
2 to the 6.
the largest power of 2 you can get, which is exactly 2 to the 6 or 64. That's 64 plus 8. Oh, so we're done. So this is 2 to the 9th plus 2 to the 6th plus 2 cubed. So this is 584 as a sum of distinct powers of 2. And the theorem says this is always possible. So this is the theorem. Every positive integer is uniquely the sum of distinct powers of 2. And the proof will be by mathematical induction. So this is an existence and a uniqueness theorem. It says for every positive integer, there exists distinct powers of 2 that add up to that number, that add up to that integer. And uniqueness says those powers of 2 up to order, because you can write them and rearrange the order, but up to order, they're the same powers of 2. So let's prove that. Proof. So let's see. My assertion, S of n, is the statement that n is the sum of distinct powers of 2. So for S of 1, 1 is 2 to the 0. Right, so it's true. Actually, I'm going to prove it. I'm going to set it up slightly differently. This is okay, but I want to use a different induction proposition, a different statement n. So I'm going to use, let's say, I don't have to use the letter n. I'm going to use, well, I use the letter n. Well, I'll use the letter k. S of k will be the assertion that every positive integer n up to 2 to the k is the sum of distinct powers of 2. So what is, when you let k equal to 1, what does S of 1 say? Every positive integer n less than or equal to the 1, which is 2. So it's saying that every number up to 2 is the sum of distinct powers of 2. Well, that's true because 1 is 2 to the 0 and 2 is 2 to the 1st. What would this statement say for k equal 2? It says every number n less than or equal to 2 squared or 4. So here we have 1 and 2. We now have to consider 3 and 4. Well, 3 is 1 plus 2, which is 2 to the 0 plus 2 to the 1st. And 4 is 2 squared. So that's true. So let's assume the statement is true for k, and we must prove it for k plus 1. So let n be an integer such that 1 is less than or equal to n, is less than or equal to 2 to the k plus 1. We have to show n is a sum of distinct powers of 2. So we're okay for every n up to 2 to the k by the induction hypothesis. We're assuming that every number up to 2 to the k is a sum of distinct powers of 2. So we only have to consider numbers that are bigger than 2 to the k, but not bigger than 2 to the k plus 1. So consider numbers n, which are bigger than 2 to the k, but less than or equal to 2 to the k plus 1. So what can we do? Well, so if n is between 2 to the k and 2 to the k plus 1, if you take n minus 2 to the k, this is bigger than 2 to the k minus 2 to the k. This is bigger than 0. Or another way of saying that n is greater than 2 to the k is that n is greater than or equal to 2 to the k plus 1. So n minus 2 to the k is greater than or equal to 1, and less than or equal to 2 to the k plus 1 minus 2 to the k. But 2 to the k plus 1 is 2 times 2 to the k. And 2 times 2 to the k minus 2 to the k is 2 to the k. So this number n minus 2 to the k is less than or equal to 2 to the k. Therefore, n minus 2 to the k, because it's less than 2 to the k, is a sum of powers of 2. You can write this as, let's say, 2 to the a1 plus 2 to the a2 plus 2 to the a sub I. Every number between 1 and 2 to the k is a sum of powers of 2. So n minus 2 to the k is a sum of powers of 2. So n is equal to 2 to the a1 plus 2 to the a2 plus 2 to the a sub I plus 2 to the k. Let me make one small change in this proof, which might make it a little bit clearer. Let's say that S of k is the statement that every positive integer less than or equal to 2 to the k minus 1 is the sum of distinct powers of 2. So S of 1, when k is equal to 1, 2 to the 1 minus 1 is 1. So S of 1, this we just have to consider n less than or equal to 2 to the 1 minus 1, which is 1, and 1 is 2 to the 0. S of 2, we would look at integers n, less than or equal to 2 squared minus 1, or 3. And we just have to look at the numbers 2 and 3, because here we have 1. 2 is 2 to the first power, and 3 is 1 plus 2, which is 2 to the 0 plus 2 to the first power. So now assume the statement is true for some k, and we want to prove it for k plus 1. So if you're trying to prove this for k plus 1, you're looking for integers n between 1 and 2 to the k plus 1 minus 1. And we know this statement is okay for n less than or equal to 2 to the k minus 1 by the induction hypothesis. So now we have to consider numbers that are between 2 to the k and 2 to the k plus 1 minus 1. And for such numbers, if you subtract 2 to the k, n is less than or equal to 2 to the k plus 1 minus 1 minus 2 to the k, which is 2 to the k minus 1. And for every such number, n minus 2 to the k is the sum of these distinct powers of 2. So n is these powers of 2 plus 2 to the k. So this is the existence half of the proof. So we prove that every number n can be written as a sum of distinct powers of 2. So a1 less than a2 less than a sub I. Must prove uniqueness. So suppose we also have n is 2 to the b1 plus 2 to the b2 plus 2 to the b sub j, where these b's, these exponents are increasing, they're distinct. And not necessarily the same number. Here we have I powers of 2, here we might have j powers of 2. So suppose we have these two different representations of n as a sum of distinct powers of 2. We must show that the number of powers of 2 is the same, I equals j, and the powers are the same, ai equals bi. Sorry, I did a different subscript. AK equals bk for k going from 1 up to I. Well, what can we say about sums of powers of 2? What happens if you add up the first m powers of 2? This is equal to 2 to the m plus 1 minus 1. That's a geometric series. You use this in calculus when you're doing integration. Sum of the first m powers of 2 is 2 to the m plus 1 minus 1. Here we have two representations of n. Suppose the highest power of 2 is different. ai is different from bj. Well, if they're different, one's less than the other. So we can suppose that, let's say, ai is less than bj. Then what can we say about n? N is 2 to the a1 plus 2 to the a2 up to 2 to the a sub I. This is the largest power of 2. So these are the smaller powers of 2, not necessarily all. If we put in all of them, we have 1 plus 2 squared, all the way up to 2 to the ai. This is just a bigger number, because I'm adding some powers of 2. And this is 2 to the ai minus 1. On the other hand, n is equal to this, 2 to the b1 plus 2 to the b2 up to 2 to the b sub j. And if I throw away all of these earlier numbers, this is greater than or equal to just 2 to the b sub j. Sorry, this is ai plus 1 minus 1. This is greater than or equal to 2 to the bj. But bj is greater than ai. That means ai plus 1 is less than or equal to bj. So this is greater than or equal to 2 if I make this exponent possibly smaller, ai plus 1, which is certainly bigger than 2 to the ai plus 1 minus 1, which is greater than or equal to n. And this is a contradiction because I have n is strictly bigger than n. That's a contradiction. So the contradiction came from assuming that ai was different from bj, so therefore ai has to equal bj. So if you have two representations of n as a sum of powers of 2, the largest power has to be the same. But then n minus 2 to the ai is the sum of the earlier powers of 2. But this is the same as ai. This is 2 to the b1 plus 2 to the b sub j minus 1. And now I have two representations of n minus 2 to the ai. These are the largest powers of 2, but these have to be the same exponents. So we can cancel them. And we can work our way down step by step. And we see that all the powers are the same. So this is the argument of the uniqueness of the dyadic, the two-adic representation of an integer. Okay. Well, these are just examples of proving results in number theory using mathematical induction. And the minimum principle and the principle of mathematical induction, which are equivalent, we use all the time in this course. So if you have not had a proof-based mathematics class, this is the first time you're taking a course which uses proofs as an essential part of the material. It takes a lot of time and effort to learn how to think in this mathematical way. And I think I'll stop at this point it's a little bit early, but at this point, because it's the first lecture and there really is a lot to think about if this is new to you. I'll be posting an assignment later this afternoon. The video will be on YouTube fairly soon. And we have our next class on Wednesday. In each class, I start by asking if you have questions. So I encourage you to study the material and to begin to look at the homework problems and ask questions if you have questions. Next Monday is Labor Day. There's no class, but I will also have a problem session sometime later this week. I'll maybe set it in the evening around 7 o'clock to make it accessible as I can. And that's the time to and I upload my notes.
So, Professor, you don't have no like set schedule where we could meet for like say extra help?
So I will have a regular schedule of office hours, but that I'll post sometime after Labor Day. But I will have at least one session later this week when I'm online as a kind of office hour. And I'll send an email. I'll post it as an announcement on Blackboard. As far as the notes go, everything is in the book. So you have the text, the notes, which are basically the textbook, which is on Blackboard. And you have the video, which will be available on YouTube fairly soon. Any other questions before we quit for the morning?
Is it possible that you can show us how to use Maple for those who downloaded the app?
Yeah, I will have a session on Maple. Certainly long before there'll be anything like an assignment using Maple. And it may be, I have to think about this, and maybe the Maple will be sort of like extra credit assignments because I don't know. But Maple is a very powerful program. It's used not just in calculus, but number theory, linear algebra. It's very, very useful. It's valuable to know how to use it. But I will have at least a class and a video on how to download Maple and how to use it. Yeah. Okay, everyone, enjoy the rest of the day. Be back on Wednesday.
Have a good one, Professor.
Thank you. Bye.
Thank you.